Welcome to this explainer on B2.3.3 looping structures. Let's think about doing chores for a second. Imagine having to wash 100 plates, one by one, and for every single plate, you literally have to tell yourself the exact same instructions. Pick up plate, scrub plate, rinse plate, set down plate. It's exhausting just thinking about it, right? Well, in programming, writing the exact same code over and over again, it's just as tedious. It's wildly inefficient and it bloats your programs. So today, we're going to learn how to stop doing the manual labor of coding. We're going to build these incredible logical engines that do all that repetitive heavy lifting for us.
Here's our roadmap for today. First, we'll look at the core of looping. Then, we'll break down counted loops, followed by conditional loops. After that, we'll dive into controlling loops with conditions, and finally, we'll wrap up with tracing and avoiding errors. Let's get into it.
Section 1. The core of looping, the engine of code.
Okay, so let's dive right into this. What actually is a loop? Fundamentally, it's just a structure that repeats a block of instructions until a specific limit is reached or a certain condition becomes false. And honestly, this simple concept is a total game changer. By running a block of code multiple times, a loop drastically cuts down on repetition. Think about it. A loop can do in 3 lines of code what would literally take you 3 million lines of manual typing. Your programs instantly become shorter, cleaner, and way easier to maintain. But like any powerful engine, it needs to know when to hit the brakes. That limit or that condition is absolutely crucial.
Every single successful loop operates on a very specific cycle made up of 4 foundational steps. First up, we've got the start values. This is where we set the initial state of our engine. Second, we check the condition, basically asking the computer, hey, should we keep going? Third, if the answer is yes, we run the body, which is where the actual work gets done. And fourth, we update and repeat. We change a value and we loop right back to step 2. Every loop needs a solid control mechanism handling these exact steps. If it doesn't, well, your output's going to be wrong, or worse, the program might literally never stop running.
So to manage all that repetition, we generally use 2 distinct types of loops, depending entirely on what we need. On one side, we have counted loops. You use these when you know the exact number of repetitions right from the start. On the flip side, we have conditional loops. With these, the repetition depends completely on a test becoming true or false. You'd use a conditional loop when you have no idea how many times the loop actually needs to run beforehand. Let's break each of these down a bit more.
Section 2. Counted loops explained. Knowing the limit.
Imagine you need to check every single item in a virtual shopping basket. Or maybe you want to print out a set of multiplication tables. You'd use a counted loop, just like the Python snippet we have here. For I in range 5, print I. Because we actually know our limit in advance, which is 5, we can use this exact structure. The loop variable, I in this case, updates automatically, following a fixed pattern. It's incredibly efficient because the structure itself is handling the start, the condition, and the update all jammed into that single first line. But you still have to be super precise. The critical components of a counted loop are your starting value, your stopping value, and your update step, and they all matter immensely. Get just one of these wrong and your loop is going to go off the rails. You know, there's actually an old joke that says there are only 2 hard things in computer science: cache invalidation, naming things, and off by 1 errors. It's funny because it's true. If you start at 1 instead of 0, or if you stop at 5 instead of 4, your entire data output shifts, and that can easily break your whole program.
Section 3. Conditional loops explained. Waiting for a state change.
All right, let's shift gears. What happens when your program doesn't actually know in advance how many times it needs to repeat? Well, here's a perfect example using a Python while loop. We're checking if the variable password is not equal to IBDP 2026. As long as that condition remains true, meaning the user hasn't typed in the right password yet, the loop is just going to keep asking for the input. We literally have no idea if the user is going to get it right on their first try, their 5th try, or their 50th try. The loop simply keeps running while the condition stays true, and it waits for a specific state change to finally break it.
And because they're designed to wait for a state change, conditional loops are absolutely perfect for a lot of real-world coding scenarios. They're basically your go-to choice for input validation, exactly like our password example. They also drive menu systems, keeping a menu on your screen until you actually select exit. They are the core engine of game loops, keeping the game running until your character loses all their health. And for sure, they're ideal for search algorithms, just looping through data until a specific item is found. In all of these cases, you're just waiting for the user or the program itself to trigger a change.
Section 4. Controlling loops with conditions, the gears and brakes.
Okay, so now that we understand the two main types of loop engines, we need to pop the hood and look at the internal mechanisms that control them. How do we actually tell the computer what condition to check? We do this using operators. Relational operators compare values. They let us check if something is less than, greater than, equal to, or not equal to something else. Boolean operators, on the other hand, let us combine or alter those checks. And means both conditions have to be true to proceed. Or means at least one condition must be true. And not simply flips a Boolean value around. Put them together and they give us total, precise control over our loop's logic.
Let's see how this all builds into a slightly more complex statement. Check out this combined condition snippet. While mark is less than 100 and mark is not equal to 50. This single while condition is governing the repetition using both relational and Boolean logic at the exact same time. It sets a ceiling. The mark has to be under 100, but it also adds a very specific exception. The mark cannot be exactly 50. If both parts of this AND statement are true, the loop runs. But if the mark hits 50, or if it hits 100, boom, the loop stops. It's a really precise level of control.
Section 5. Tracing and avoiding errors, the test track.
Look, knowing how to write a loop is really only half the battle. The other half is actually making sure it works right. We have to take our coding engine to the test track by tracing the code. This lets us see exactly how variables change and helps us avoid catastrophic program failures. Let's look at this tracing example. We start with a total of 0. Then we've got a counted loop for I in range 1 to 5. Inside the loop, we update the total by adding I to it, and then we print that new total. Now, a super crucial thing to remember about Python is that range 1, 5 generates numbers starting at 1, but it stops just before 5. So we're specifically looking at the sequence 1, 2, 3, and 4. Let's actually map out the computer's memory step by step. We're going to walk through this trace table slowly. In iteration 1, our I is 1. The total updates to 0 plus 1, which gives us 1. Moving to iteration 2, I becomes 2. Our total updates to our previous one plus this new 2, making it 3. In iteration 3, I is 3. The total is now 3 plus 3, which is 6. Finally, in iteration 4, I is 4. The total becomes 6 plus 4, giving us 10. And that's where the loop ends, because we've exhausted our range sequence, leaving us with a final printed output of 10. Tracing like this is basically a superpower. It lets you see exactly what the program is doing at every single microsecond.
And tracing? That's exactly how you catch the ultimate villain of programming, the infinite loop. An infinite loop is a rogue program that literally never stops running because the condition telling it to stop is just never met. So why does this happen? Well, it's usually one of 3 missing pieces. First, the condition is written in such a way that it simply can never become false. Second, the update statement inside the loop is entirely missing, meaning the state never actually changes. Or third, there is an update statement, but you're updating the wrong variable. That leaves your loop's control variable stuck at its starting line forever. So the big takeaway here is that you defeat these errors by being absolutely meticulous. How do you avoid infinite loops and those pesky off-by-1 errors? You trace your code by hand, exactly like we just did with the table. You test edge cases, like what happens if the user inputs a negative number or a 0. And especially in languages like Python, you check your indentation carefully. If you put an update statement outside the loop's indentation, it's never going to run during the repetition. Mastering this tracing skill isn't just good practice, it's absolutely essential for your IBDP exams.
To wrap up our explainer today, I want to leave you with a bit of a provocative thought. Imagine you are programming the software for a self-driving car, or maybe a medical life support machine. How would you bulletproof your loops to ensure they never ever go rogue? The next time you sit down to write a loop, I want you to trace it, test it, and honestly ask yourself, is my engine truly under control? Thanks so much for hanging out with me today, and keep coding.